Ignition sequence start. 6, 5, 4, 3, 2, 1, 0.
Hello and welcome back to another edition of Ignition Sequence. I'm John Murphy, and we're about ready to start several episodes dealing with the evolution of Earth's atmosphere and climate over the past 4.6 billion years. In this episode, we'll begin with the Hadean Eon, or some say the Hadean Eon, the earliest chapter of Earth's history. For years, scientists imagined the Hadean as a fiery, desolate hellscape, a time when Earth was bombarded by impacts, covered in molten rock, and far too hot to support water or life. But new evidence suggests that this might not be the whole story. Some intriguing discoveries are challenging that view, hinting that Earth may have had liquid water in even more temperate conditions much earlier than we ever thought. Joining us to unravel this mystery is Dr. Mark Harrison, a leading geochemist who has spent his entire career studying the early Earth. Mark's going to help us explore what the Hadean Eon was really like and what these new findings mean for our understanding of Earth's ancient history. And welcome, Mark, to the show.
Well, thanks for inviting me. I'm looking forward to it.
He is a distinguished professor of geochemistry in the Department of Earth, Planetary and Space Sciences at UCLA. He has since retired. But listen to this. He has published over 260 papers and books. You know, I don't think Stephen King and James Patterson combined have 260 books and papers published. Where do you find the time to do all that?
Well, I don't think they write too many books that are 9 to 11 pages long, so that helps.
His range of topics include magmas, geochronology, interpretive models for heat and mass flow, the evolution of petroleum reservoirs, geothermal systems, and investigations of the very, very early Earth. This is really, really fantastic stuff. But first of all, tell us, what is a geochemist? I know there's different disciplines under the field of geology, so tell us, what is a geochemist?
Well, it's somebody that is obviously interested in the origin, evolution of the planet, but takes a page out of the books of the chemist, and we use those methods to learn about, for example, how old the Earth is, how the Earth differentiated, produced these different layers, the core, the mantle, and this crust that we're standing on now. And you can learn so much about the structure of the Earth today, say from geophysics, looking at what the present structure is. But the geochemistry is what's going to give you this long, deep time element. We can look back 4.5 billion years to reconstruct what's happening then.
And you're talking about 4.5 billion years. You're talking about the Hadean Eon, or is it the Hadean Eon? Which way do you say it?
Well, the planet is 4.5 billion years old. The first 500 million years, we don't have a macroscopic rock record of that. The Earth is in the business of destroying evidence of its past existence. Plate tectonics, as I say, eats its own evidence. So we don't have any rock that you could hold in your hand that's older than 4 billion. But we do have tiny little grains of zircon, a very hardy mineral. We find little bits of it in sediments, and some of those grains get as old as almost the age of the Earth. They get back to almost 4.4 billion years. And those zircons have a story that's locked up in them. And so the geochemist's job is to go in and translate those signals, the chemical signals, to understand early Earth environments.
Was the actual time stamp of the Earth being 4.5 billion years old, was that taken from examining meteorites
Yes.
and looking at how old
Right.
that organic material is?
Yep. Yeah. Meteorites, these are objects that are, flying in every day and night. We find that, they've been in cold storage for the most part for the whole 4.5 billion years, whereas Earth is dynamic. It's, continually repaving itself. So we have this clear record of the stuff that we were made out of 4.5 billion years ago. And we can infer, unless we were to take the entire planet and crush it up in a giant mortar and pestle and then analyze it, we're not going to be able to date the Earth itself But there's enough similarities with the building blocks, these meteorites that we see, that have mostly come from the asteroid belt, for us to be able to infer that, yeah, indeed, we all started, us and the asteroids, 4.5 billion years ago.
Fascinating. Before we get into a deep dive in the history of the planet and how it became a water-based planet, how did you even get involved in this? I mean, because it's so specific, it's so deep and very complex. What drew you into this field of study when you were a little kid? What was it that rocked your boat, so to speak?
Well, I'm not the best example. You ask 4 physicists how they came to physics, and they're going to tell you pretty much the same story. Okay, they did well in high school. They went on, got it. You ask 4 geologists how they got into the business, and you'll get 3 different answers. Okay, so for me, I was thrown out of college as a teenager. I kicked around the world for a few years. I discovered a love of geology, doing various technical jobs in the Southern Hemisphere, in Australia and Africa. Then it's time to go back to school, and I did so with a vengeance, and that was 50 years ago.
But what was it that just really pulls you into this specific field?
Well, in fact, I came in relatively late. We developed an instrument, which was, globally unique at the time, a thing called an ion micropro. Basically, it's a big device that's able to date little bits of minerals that are 1/10 of the width of one of the hairs on your head. So it turns out that, having a rock this big can actually, if you ask that rock how old it is, it can give you multiple answers. But when you get down to the smaller and smaller scale, the answers become clearer and clearer. So it was effectively the instrument capability led us to, ponder questions that before that device was commissioned, that you couldn't. It's like an astronomer getting a telescope that can see 10 times further. They're going to discover things not because they were looking for it. They're going to discover things because they were there, and they now have the analytical capability to detect them. And that's how I got into this business.
Yeah, it's very exciting. I mean, it must be really fascinating to discover things maybe for the first time that science and the community and research has never uncovered before. That's the job, right?
It is. And what I say to my incoming graduate students is that, in a sense, you're here to not just see whether you have a talent in research, but also to see whether the payback is sufficient. Because in my experience, those sorts of discoveries, they come, if you're lucky, once every 2 years, maybe, and all that dog work that you have to do, all the data that needs to be generated, it can seem a little tedious. But when you have experienced the thrill of discovery, like, good heavens, the planet is actually a lot different than what I was told when I was an undergraduate. That motivation that kept me going for those years. And it's, you look at students come in, some of them have that experience of discovery, and it's like, well, that was great, but I think I'll go and make money.
Yeah.
So it's not everyone. This job isn't right for everyone.
I understand that Earth is broken up into 4 separate eons. And you wrote a book about the very first eon, the first 500 million years. Now, and I asked you earlier, you didn't quite answer the question, but is it Hadean or Hadean?
Hadean.
Hadean.
Yeah, and it's from the biblical term that meant a hellish origin. For the long time, my community, my scientific community, basically, imagined the first, maybe even billion years of Earth history to be this hellscape: no continents, no oceans, no life. And what we're learning as we get little bits of, a little lithic record from that first 500 million years, is that actually it was probably a lot more like today than we long thought. So the name Hadean is fun because it actually comes from the Greek myth, when, of course, Hades was a watery, you had to cross the river Styx, and it was really only with the publication of the King James Bible that this the various ways you might describe hell in Koine Greek, got turned into the concept of a fire and brimstone hell. So my community adopted the word because they assumed that early Earth was hellish in the Bible, in the King James version of the Bible. But I think it's turning out that it's actually more like the original Greek myth, which is the fact that it was a wet place.
That's crazy. What was it that kind of pivoted that long-held belief that it was this fiery hellscape, Hadean, as you say, into a water-based kind of planet? And the big leap is, how does something that has so much fire and heat and everything as it's developing from the Big Bang, how does it even form water? Where does that even begin?
Well, water is the most abundant triatomic molecule in the universe. So there's lots of it around. Our problem wasn't that there wasn't a lot of water around when, the solar nebula in this neck of the galaxy was collapsing to produce our solar system. There was lots of water around. Problem is that then in this neck of the solar system, around 1 AU, right, 93 million miles from the sun, all our calculations suggest that this was a really dry place, that if we had water, we would have lost it in this energetic, hot region of the early solar system. So the puzzle has not really been, why was there water? You look at the giant planets, there's a lot of volatile material there. It's how did it get in here? So that's been most of the effort to understand how you would perturb objects in the outer solar system, maybe comets, maybe volatile rich asteroids, and so on, to come in after Earth forms and deposit the water. So there's almost universal agreement that our oceans, our water, is secondary. That the planet formed, and then we got the water seeded to us by these objects in deep freeze out in the giant planet region.
Is this part of that bombardment period that's talked about a lot? This the heavy bombardment of just meteoroids and asteroids and things like that just pelted the Earth constantly?
Well, in fact, you say the late bombardment is a concept that arose actually out of the Apollo era explorations, and a large number of people in the lunar science community, frankly, misunderstood the significance of the dating that had been going on those Apollo return samples, and developed a concept called the late heavy bombardment. And that is about 3.9 billion years ago, so say 600 million years into solar system evolution. We got pelted with lots and lots of objects, and you look up at the moon, and some of those big impact basins on the near side, they're around that age. We still don't know exactly how old, but we would have been bombarded 20 times more than the moon because of our bigger gravitational cross section. So it must have been, a pretty energetic time. Except there's now growing evidence that the late heavy bombardment may not have ever occurred. So what was once thought as a possible source of our water is probably an event that may be an illusion. Nonetheless, the early solar system, there was a lot of space junk out there, and for the first couple 100 million years, maybe not 600, but the first 100 or 200 million years, all the planetary objects were sweeping up this debris. And it would have been, I would not have been safe to go outside, say, 4.4 billion years ago, at least not for us.
That's what I love about science. It's this constant flow of argument and debate, because, you lock onto an idea and the science community embraces it, and it becomes written up in papers and becomes kind of the base standard of understanding, and then something else happens. Is, oh no, what we thought was completely wrong. Completely wrong. How does that make you feel as a scientist? That's part of that discovery journey.
Well, it's verification that separates our religion of science from all the other ones.
And I like that you say the word religion, because I watched one of your lectures. You were a guest lecturer online, and you talked about the biblical Genesis. God created the heavens and the earth in 7 days. You talked about how there's a whole, millions and millions of people who believe the earth is only 5,000 or 6,000 years old, but there's no verifiable proof to support that argument. But neither is there verifiable proof that the Hadean era, the first formation of the planet, exists, because the Earth, as you said at the top of this podcast, destroys its evidence. And I thought that was a brilliant connection.
We have, scientific humility is an important trait for all of us to buy into. And in my business, I want to know where Earth's water came from. I want to be certain when plate tectonics began, but it isn't up to me. And working even harder, it's up to the rock record. If in fact the planet has eliminated all rock record from a particular time period, then these questions may not be answered for some time. I mean, just to digress momentarily, it may be that the answer to the questions that we're going to talk about today, where does Earth's water come from, are actually on the moon, because 4.45 billion years ago, the moon was 10 times, 14 times closer than it is now. As I said, there was stuff raining in left and right. There's actually a lot of terrestrial material that would have been sprayed onto the moon. So one of the reasons to go to the moon, from my perspective, is it may be that the answers are preserved up there in deep freeze, where in fact they've been, thrust back into the mantle and homogenized and don't exist on this planet. So to learn about where we come from on Earth, we might have to go to the moon.
The moon was formed during the Hadean eon, I believe. Can you explain that to us? How did the moon come to orbit the Earth?
Well, there's a broad agreement that there was some form of maybe the Earth was spinning very fast, maybe whether a glancing blow or a nearby impactor or a direct hit. There's about half a dozen models that I think could satisfactorily explain what we know. The composition of the Earth and the Moon. We're twins. Okay, we're fraternal siblings. Okay, so there's no question that we're the same stuff. How that stuff got out there, as I say, there's a half a dozen models. What's interesting is the one that, if you ask a person on the street, the Mars-sized impactor, that's actually the one where I'm pretty certain can't explain the origin of Earth and Moon, because that model, in its original form, predicts that the moon should be 70% or so of the impacting object, that Mars-sized object. And the likelihood that whatever hit us to make the moon was an identical isotope composition is vanishingly a small probability. So we don't yet know, but there's general agreement that there was some interaction with some body in the inner solar system that took material from the proto-Earth and put it into lunar orbit.
You said that when the moon first came into being, that it was 10, 15 times closer to the Earth than it is now?
Yep. Yeah, that's right. And it continues to move away from us. Every time you go to the beach and see a tide raised, that's pushing the moon further further outboard. So and of course now there's not that many impacts in the inner solar system. Now the moon's that much further away. Let's say early on, the moon might actually have a high fidelity record of the Earth's impact history, and maybe when did plate tectonics? Questions like that can be really resolved by extensive lunar exploration.
That was one of my fondest memories as a kid. It's when Neil Armstrong walked on the moon. And I distinctly remember literally watching it on television. I was living in El Paso, Texas at the time. And the time that it was dark, and I could run out and see the moon. And then I ran back in and saw him on television. Then I ran back out, looked at the moon, and thought, holy cow, there's a guy up there, and I can see him on my television, but he's up there. It was just amazing.
Yeah, and what's even more wonderful is that within a couple of years, we'll have a gal up there.
Yeah, for sure. And you're not a conspiracy theorist. You think it actually happened, right?
Well, I mean, I say science is not about knowing the truth. It's about, estimating probabilities. And I would say that the likelihood of you being able to maintain that conspiracy of 50 years later is practically zero. It would be easier to go to the moon.
Very good. You wrote a book in 2020 about the Hadean Eon, but it's like what, 900 pages long? Something like that?
No. I don't know. It's 280 or something.
Oh, is that it? Wow.
Yep. Well, I mean, we this is a eon of Earth history for which we have no macroscopic rock record. I mean, how long could it be?
Right. Well, that's true. That's true. Can you encapsulate the book for us? Kind of what was your point of writing it, and what theories or things were you trying to get out of it?
Well, what I wanted to do was to summarize. There's really 4 different ways we can learn about Hadean Earth. Okay, this is that first 500 million years. It's an informal term. It's my definition is it's the period of Earth history for which we don't have a documented macroscopic rock record. So the oldest known rock is from northern Canada. It's about 4 billion years old. So from the time Earth forms at about 4.5 to 4 billion, all we have are these tiny little zircons I mentioned earlier, zirconium silicate. It just turns out to be this wonder mineral because it's very robust. It's hard to kill a zircon. Okay, so they want to preserve. The zircons are forever, and they love to concentrate uranium. And uranium decays to isotopes of lead at a known rate, so we can use those minerals to determine accurately and precisely how old these grains are, and they turn out to be almost 4.4 billion years old, as that. So, the most amazing thing about the, Hadean science is the fact that we're talking about it. Okay.
Right.
Nature has conspired to, but there's 4 ways that you can, understand the Hadean. The first is simple physical laws. We're physical scientists. We assume that physical laws are constant through time. So we can take simple phenomena like radioactive decay, and if decay rates are constant over time, which as a point of faith we take, there's no evidence that they're not, then we can say, look, there must have been 4 or 5 times more radioactive heating in proto-Earth or early Earth than there is now. So that's useful. Oh, it must have been hot. There was some real energetic sources. The second way is during that early creation of the planets, there was short-lived radioactivities around. They were produced in a supernova not too far away that injected freshly baked elements and isotopes, some of which are radioactive, and they produce a very distinctive signal that is preserved in mantle rock. So, for example, a volcano erupts on Big Island, Hawaii. We can sample what the Earth's mantle is like. And when we look at rocks that come from the mantle, as you mentioned earlier, we've got a core, basically a stainless steel core in the center, a rocky mantle, and then this flotation scum up here that, we call the crust. So when we get those mantle rocks, they're telling us that something pretty profound happened in terms of separating the metal from that silicate mantle early on, really within tens or hundreds of millions of years of Earth formation. So that's pretty good. Now, the third method we've already talked about. It's, the moon has basically been a storage for us in terms of what the impact history of the inner solar system was. We spent a lot of time misinterpreting it from my point of view. But nonetheless, there's valuable things that can teach us about what that first 500 million years was like. Because, say, we have minerals and rocks from the moon that are 4.4, even almost 4.5 billion years old. And the last way, the fourth way, is these little zircons that we've discovered. In fact, it was a discovery made in Australia in 1983. And it was seen at the time as, just sort of a freakish curiosity. They couldn't possibly be telling us what the planet was like, because at the initial glances, this comes from a rock that looks a lot like, that mountain over there.
Well, that's what I was going to ask you. How do you know it's a zircon? And how can you discern from just any other part of the rock? Oh, this is a zircon. It's 4.5 billion years old. Let's examine it to see, what we can find. How do you even know? How do you even find it?
Well, in fact, I mentioned that these little grains are found in younger sedimentary rocks, most sandstones. Imagine, where are you right now, John?
Well, I'm in Los Angeles.
You're in Los Angeles. Okay,
right.
Bad example. Imagine Bologna Creek is flowing into Santa Monica Bay, right?
Right.
Bologna Creek is not crystalline clear blue water. You know that. It's kind of a mucky brown color, and that's because there's bits of sand in there, bits of silt. And in there will be, in any hand-sized batch of sediment coming through down Bologna Creek, there'll be a zircon, because, as I said earlier, zircons don't want to die. They're very robust. They're also heavy. They've got a very high density. And so when we go and look at ancient sedimentary rocks, say ancient sandstones, the zircons, when they settle out of suspension, from the creek flowing into Santa Monica Bay, even the fine particles are eventually going to settle. They're going to settle with other dense grains like chromite, chromium oxide. It's very dense. So the zircons and the chromite find themselves sitting next to each other. And then when you metamorphose, when you apply a little heat and pressure to that rock, the chromite, the chromium oxide, actually turns into a mica, those platy minerals, that's green. So as I go and look at these ancient sedimentary sequences for old zircons, I look for green rocks. I look for the mineral called fuchsite. And it's a great indicator that the zircons are going to be nearby. We'll get that rock, bring it into the lab, we crush it up. It's dirty work. Put it in a very dense liquid, and only those heavy minerals separate. The zircon comes down. So all of a sudden I can take, really something, a rock this big, and I can come away with a separate that would sit in the palm of my hand like that. That's maybe 50% zircon. Then we'll mount those zircons. Even in our richest Hadean zircon mine in Western Australia, only 2 zircons in every 100 that we find are Hadean. So we then have to use, remember I mentioned earlier that ion microprobe? We could put that tiny little beam and date that stuff. We will systematically, we've had to date 200,000 grains of zircon from our, in order to get a couple of thousand that are Hadean. So it's a needle in a haystack problem. So it's a good question, because that is the principal reason why this discovery came so late was, one, it needed a new analytical capability. You take a rock this big and you crush it up and you analyze it, you will never see an age that old. You have to get down to let's say a length scale smaller than the width of one of the hairs on your head in order to begin to see these little ancient grains. So now we've got them, we've identified them, we can do experiments on them, and when we ask appropriate questions, the zircons, to me, are screaming, there was continental crust, pretty much just like we see around us today, 4.2, 4.3 billion years ago. And of course, that came as a rude shock to the community.
Right.
It's very controversial today. But what isn't controversial is that those little zircons were able to winnow information out in a couple of different ways that suggest there has to be lots of water, immense amount of water at or near the Earth's surface in the Hadean between, say, 4.4 and 4 billion years ago. And that was a radical departure. Remember, from our original hellscape, we called it the Hadean because there were no oceans. It was an arid, desiccated, dead body. And now we're starting to see rocks and isotopic signatures that are basically very similar to what's going on in the Ring of Fire around the Pacific today. The same sorts of processes in the Ring of Fire are embedded signatures in those Hadean grains.
Am I being too simplistic? I'm just in my head, I'm drawing this kind of correlation between the discovery of the human DNA genome and, it's like you're finding the DNA of Earth. You're finding the source material of the planet. Is that too simplistic? Is there a correlation like that? Or
let me put that in background and see if I can think of another analogy. I mean, again, this is, imagine you may like to watch detective procedurals on TV. I mean,
sure.
What we do is what they do. Bump, bump. I can't solve this murder unless I get the evidence.
Right.
And nature is trying to not give us the evidence, so it's really hard to move this problem forward. And in the absence of things moving forward, we as a community have kind of mythologized a little bit, and we need to, remember that our models aren't true. They're models. They're our way of trying to understand reality. But these questions of origin versus water and the nature of the Hadean, I say the remarkable thing is that we're even talking about it. Not that we've got 100% agreement on what actually happened.
Were you saying it's controversial? What's so controversial about it? I mean, I know it upends your scientific paradigm that you've been latched onto for years, right?
Well, imagine that you have latched onto a paradigm and you're, repeating the tribal chant, as you go to international meetings, and guy comes up and he says, I've been talking to these zircons, the entire population of which would fit in this palm of my hand right here. And I'm telling you that this was what Earth was like 4.3 billion years ago. I mean, a reasonable response would be, who's to say that your zircons are globally representative of what was going on? And, there's no answer to that. I don't know. What's ironic is that when there's 15 other locations on the planet where we know of Hadean zircons. And we've gone to great lengths to try and characterize these other locations, but we keep coming up empty on funding because the reviewers come back and they say, well, this is a fishing trip. He can't guarantee that he's going to find Hadean zircons in that location at the abundance level that he found in Western Australia, and that's absolutely true. But it reflects the fact that our national science funding is largely hypothesis driven, right? And we're comfortable, but you don't justify the next telescope based on what you're going to find. You build the next telescope so you can find what you don't know. And the same is true in my business, that it's a very conservative culture, and risking significant funds to find something that you can't guarantee is a difficult ask.
So you found these zircons in Western Australia. I think they've been identified in rocks in northern Canada, up in the upper territories. What are some of the other regions on the planet? And is it all quadrants of the planet that you believe these zircons exist?
Well, they are now, but where were they 4.2 billion years ago? If you do, we can probably reconstruct where the continental nuclei, where Central North America, where Western Australia, where Southern Africa, we can reconstruct these back to about maybe 2.8, 2.9 billion years ago. And 2.9 billion years ago, these 15 different locations where we recognized Hadean zircons, at least one Hadean zircon, they're pretty disparate. So it probably was, they probably were well separated, but where were they 4.2 billion years ago? maybe there was a single, continent the size of Los Angeles County, and that broke up and produced nuclei that made Southern Africa, North America, Siberia, etc. So these are issues that we may never be able to satisfactorily address. But let's keep looking, and let's keep expanding the archive, because though that's that one locality in Western Australia, Jack Hills, that in my view is revolutionized our understanding of early Earth.
And I remember seeing, graphs in college and things like that where, like South America and Africa were kind of connected in that, they kind of fit together kind of nicely, very kind of simplistic little graphic illustrations. But does that theory still kind of exist, that the continental plates were all kind of together and split off?
Yeah, absolutely. That was the last time all the continents got together in Pangaea time, about 300 million years ago, and then they drifted off. It's maybe worth pointing this out that the geophysicists, when this idea was first raised, were absolutely implacably opposed to the idea of continents drifting, of the surface being mobile. So there's always been conservative reactionary forces in my business, largely driven by geophysicists who, until something is demonstrated, they can't believe that there possibly be a mechanism. So in fact, there was early calculations about fluid motion in the Earth's mantle led that community, the geodynamical modeling community, to say plate tectonics is not feasible on early Earth. And then these little zircons come along. They demonstrate evidence that, well, let me say one thing. The Hadean zircons may not be able to prove that the Earth was, as similar today as you see, at least in terms of Earth dynamics. But one thing's absolutely clear is that the Hadean zircons are completely inconsistent with the hellscape paradigm that the community was bonded to for 50 years. Okay, so I say the early calculations suggesting plate tectonics couldn't possibly happen on early Earth, I think stunted the dialogue and prevented us from moving this problem forward. Because when the Hadean zircons were discovered, there was a tremendous backlash, or a tremendous effort to minimize their importance. That these can't be geodynamically important because we know the Earth was a hellscape. And of course, more recently, now that the computational modeling has gotten more sophisticated, now it's like, well, how would you stop plate tectonics from emerging in early Earth? And there's two thoughts on that. One group says, you can't stop it on a planet with these characteristics, and another one that says no, plate tectonics didn't start for 2 billion years. But therein lies, Robin, maybe this is a good segue to another topic, which is, what if we didn't have an ocean in the Hadean? Because right now, there is virtually a 99% consensus in the planetary science community that the reason we're not like Venus, okay? I'm looking out suburbs, the green suburbs of Richmond, Virginia here. The surface of Venus is almost 500 degrees Celsius today. So,
wow. Wow.
We're about the same position from the sun, about the same mass. Or what went wrong? And one argument is that, it's been made for 50 years, is that the reason we don't have a runaway greenhouse like Venus does, with a dense CO2-rich atmosphere, which is, basically creates this runaway greenhouse, is because of plate tectonics. That when you bring, rocks to the surface in the presence of an ocean, presence of water, the weathering of those rocks, we say subaerial, meaning, under the sky, the weathering of those rocks at the Earth's surface, in the presence of water, actually produces reactions that, one, make the ocean salty, and two, suck CO2 out of the atmosphere. Okay? They're called the Uri reaction for our shorthand. But, there's really no debate that the reason why we've been, had a moderate or temperate atmosphere, for at least since 4 billion years, is that there we have an ocean and we have exposed rock. So the people that are saying, oh, no, we didn't have plate tectonics for the first 2 billion years until 2.5 billion years ago, question that they don't generally face squarely is, how do we not get a runaway greenhouse? Volcanoes are erupting all the time. They're spewing CO2 from the Earth's interior. If we don't have a way to sequester that CO2, we are going to look like Venus before too long. So the nice thing about, and I think one of the reasons that geodynamical modelers are coming back to the idea of early plate tectonics, or coming to the idea, is that it also explains why you and I are having this conversation today. Because if we don't have the sequestration mechanism, and it's 500 degrees Celsius out there, there's no internet.
Yeah, there's nothing. There's nothing. We've talked about the plate tectonics. You explained it just a little bit, but when did the concept of plate tectonics kind of become more popular? Because what kind of proof and evidence? Because the science is always looking for actual, viable, physical, seeable evidence to kind of prove theories. What kind of evidence demonstrates that plate tectonics happens to now today, and it happened maybe 500 million years ago, or even or 4.6 billion years ago?
Well, the idea has been around for 100 years. And when it was first proposed in the 1920s, as I mentioned, the geophysical community was implacably opposed to it. And it more or less killed the idea until the 1960s. And this comes back to my point about hypothesis versus exploration science, is that basically we are in a existential conflict with the Soviet bloc. We don't want our nuclear submarines to bump into seamounts. So, the defense establishment provides money for oceanographic institutions to basically map the seafloor. And patterns emerged on the seafloor, which was in fact thought by many very distinguished people in the 1950s, as late as 1960, that the seafloor is the oldest material on the planet. It's primordial. But in fact, it's the youngest. It's forming today in places. Wow. And also because we were worried about Soviet nuclear tests, we thought we really need to know what the background terrestrial seismicity is, so we can in fact separate that from underground nuclear explosions, or above ground nuclear explosions back then. And it was when these two data sets appeared, again, not driven because any geologist went, that guy's idea back in the 1920s, that had merit. It was because complete serendipity. All of a sudden we see, wait a minute, the ocean basins are alive. They're forming and being destroyed, or destroying, being destroyed as we speak. And the record of global seismicity showed that the seismic activity is limited to, for example, where rocks are being destroyed around the Pacific Rim of Fire, or where they're being created at mid-ocean ridges. And it all fell together in just a couple of years. And once the geophysicists were on board, there were now absolutely clear reasons why this could happen.
Well, it's kind of interesting because I don't know if this has anything to do with it, but here in LA, we had a 5.1 earthquake yesterday. The epicenter was below the surface in Thousand Oaks, which is in the far west San Fernando Valley in the Los Angeles area. I live in Pasadena, a good probably 35, 40 miles away, and my house shook. I got a good little rattle out of that. Is that part of the whole plate tectonics thing?
Absolutely. That's the Santa Monica Mountains. The reason why they're there, right above UCLA, is that there's a thrust fault that runs, along Santa Monica Boulevard, and then steps up towards Sunset. And that thrust fault, here's Westwood, here's home of UCLA, and that's north, that's south, and what's happening is the fault is basically bowing those rocks into the Santa Monica Mountains, and that's where I used to live. That's UCLA, and we're very fortunate that this is happening because we get these little 5.1s periodically, or maybe even 6.8s.
Yeah.
That remind us we're
I was here during the Northridge earthquake.
Us too.
Yeah,
Yeah. We wrote it out, but it wasn't fun.
Nope.
We get these little jolts periodically, whereas up in Portland, Seattle, I think a lot of people don't understand that there's a much greater seismic risk to the Cascadia megathrust. That only happens every 300 years or so. So we're getting these warnings every few years or decades that we're in earthquake country, and our building codes reflect that. Whereas I say up in in the real dangerous area in the Pacific Northwest, there's not the same. There traditionally hasn't been the same sense of urgency. So yes, but what you're saying is what that earthquake in Thousand Oaks the other day, that was part of the global tectonic engine.
And I find it very interesting that you were a distinguished professor at UCLA, and as soon as you retire, you get the hell out of here because you're in Richmond, Virginia. It's like something. That there's going to be the big earthquake is coming, and I'm getting the hell out. Is that why you moved?
It's another proximal cause, and that is that our only grandchild, the most adorable 7-year-old on the planet, lives a block and a half away. So we spend half our time in the earthquake country in Westwood, in fact, now, and half our time out here in Richmond watching her grow up.
All right. So you're still in LA. You're still a Los Angelino. Okay. That's good. The concept that we had can you break down, just for people who may be unfamiliar, the layers of the planet? You talked about a crust. You talked about a mantle. We've talked about the core. Kind of what are the separation layers and how deep do they go?
Well, the planet's 6,300 kilometers in radius, okay? And right about here, there's a big compositional discontinuity. The inner core, the core, part of it's molten, part of it's solid. To say it's basically, like I like to say, stainless steel. It's nickel and iron and a few little light elements. And that's very different than the rocky mantle that separates the core mantle boundary from the Earth's crust. And there's two kinds of crust we've talked about: ocean crust, right? That's the stuff that's being created and destroyed as we speak in order to make the plate tectonic mosaic work. There's continental crust. This is this buoyant stuff. Imagine, we're the boogie board that's floating on top of the swimming pool, right? We're up there because we are less dense than the underlying mantle and the adjacent oceanic crust. So when that dense oceanic crust, okay, so here's my thick continent, when that dense, thin oceanic crust hits us, it loses almost 99% of the time. It gets thrust underneath. And you see what's happening. We're basically, it's a conveyor belt. We're destroying all that crust. And Earth's radius stays the same. What happens over here, okay, new crust is being made at mid-ocean ridges that then gets spread apart.
Wow.
It was the record of that was seen in those magnetic stripes that I mentioned to you in the sort of the 50s and 60s that got everyone thinking about the mobility of the oceanic crust as opposed to it being primordial. So we've got the stainless steel inner core, this rocky outer mantle, and this crust is typically, the oceanic crust is thin, 10, 12 kilometers. The continental crust is typically 30 kilometers, but in places it can be 90, 85, 90, like in Tibet. And what happens when you make that boogie board twice as high? It's going to sit up in that swimming pool twice as high. And that's why the Himalayan Tibetan plateau are up there so high, is that continental crust is so thick. It's more than doubled the normal thickness. Wow.
That is fascinating. Just utterly fascinating. I want to get back to water. There's water that we see in the oceans, but is there water anywhere else that's hidden And is Earth holding a lot more water than we realize?
Yeah, absolutely. That's a question that's being actively studied today. And we're learning a lot, really mostly from mineral physicists, people that are looking at what the mineralogy of the mantle, that rocky part of the Earth, and studying those minerals under exceedingly high pressures. I mean, pressures as high as 1,000,000 bars, 1,000,000 times atmospheric pressure. And what we're finding is that there's probably the capability of our mantle to store maybe 3 or 4 oceans worth of water in that rocky part of the Earth. There's obviously just a little over 1 ocean out here. So it would be important to know, does the Earth have 2 oceans worth of water, 3, 4, or 5?
Would they be saltwater or freshwater oceans?
It mostly actually in the form of hydrogen. So, there's so much oxygen. Oxygen, if it's not just out here in the atmosphere. The most abundant element in Earth is oxygen. So from our perspective, if you have a little hydrogen, what water is H2o, if you got a little hydrogen, there will be some oxygen that would like to make water. So when we say that we're storing, say, 10 oceans in the core, it's not water, it's hydrogen.
Got it.
So we're going to have to oxidize that in some way. In the mantle, it's often stored as not H2O, but as OH, okay? And that little OH can actually attach itself and be comfortable inside minerals that you would think otherwise are anhydrous, don't have structural water. And when we talk about 3 or 4 oceans down there, we're talking about the capacity to have 3 or 4 oceans. Not that we know that there are 3. Simply there could be. There is the storage capacity to have 3 or 4 oceans in the mantle. I'm absolutely convinced that there's at least 1 or 1.5 oceans stored in the mantle, but it could be as high as say 3 or 4. There's a lot of speculation because the core is so far away from us and difficult to study. There's a light element or light elements in the core, so there's possibility that there's an enormous amount of hydrogen, sort of unoxidized water in the core. There could be, you could speculate as much as 50 oceans of water in the core, depending on
50 oceans of water? 50 oceans.
Yeah.
Like the Atlantic and Pacific, 50 of those.
Right. No, 50 of the entire global ocean system.
The whole thing. So 50 of planet Earth's total visible water.
Surface water, exactly.
Surface water. Wow.
Yeah. So, but I say, let me emphasize, this is very speculative. There could be none. I don't think that's likely, but so what we know is there's a little over 1 ocean out here right now. You throw in the Great Lakes, and we're pretty certain. I mean, even the low estimates of how much water is in the mantle is there's at least another ocean down there with the potential storage capability of 3 or 4. And you can do some simple calculations, and if in the extreme, it appears that we probably never had more than about 1 or 1.5 oceans out here at the surface when the planet settled down after that tumultuous beginning. And so but we're almost certainly recycling this water out here back into the mantle where the oceanic crust goes down and under thrust the continents. So there's the possibility that we had as little as half an ocean in the past, or as much as 1.5, but probably not much beyond those bounds. We have evidence. The oldest known, the Hadean Zircons are telling us that there has to have been a lot of water at or near the surface between 4 and 4.4 billion years. We have the oldest known marine sediment. The oldest known sediment that formed in water is 3.83 billion years old. So by 3.83, I can hold a rock in my hand that in fact is evidence that there was a surface ocean. We see, in fact, fossil shores preserved in rock between 3.7 and 2.5 billion years. So through this eon that we call the Archean, there's evidence that I would say is compelling that we had not only surface water, surface ocean, but we also had, remember, that subaerial exposed continent crust, okay? Because we need both in order to suck the CO2 down and sequester it.
It's really fascinating. And I'm wondering what's going to happen once we fully understand the ocean floor, to finally map it all out, explore it, look at it. I think that something else will be discovered that you guys haven't even thought about yet.
Well, maybe. I mean, I'm take the opposite point of view, actually, and that is that it turns out the ocean crust is pretty simple. I mean, here's an irony. Back in, let's say, 1960, there was, a high degree of consensus in the community that we knew when continents originated and how they grew, but we knew nothing about the ocean floor. As I said, distinguished scientists thought that it was primordial, thought it was the oldest rocks on the planet. And now, even though we haven't explored every nook and cranny, we're not seeing, after 50 years of underwater exploration, we're not really learning new things. For example, 40 odd years ago, right, the discovery of black smokers, that was an astonishing discovery.
And the black smokers are, once again?
It's where the oceanic crust is separating to produce, new ocean floor.
Right.
The fluids that are circulating between, the ocean waters and the fractured rocks that are very hot produce these jets of either white or black, depending on the chemistry that's going on. And they've been found to be, habitats of species that had never before been documented. There's a very big portion of the astrobiological community that believes that life may have originated adjacent these black smoke devices on early Earth, implying that there has to have been an ocean,
yeah.
Which I'm all for. But really nothing, in the last 40 years of exploration of the ocean floor has produced such a new insight. So we've gone, to say, from the early 60s, where we thought we knew everything about continental origin and growth, knew nothing about the seafloor, and now I think we really understand how the seafloor forms and how it's evolved. But there's almost no agreement on when continents began to form and how they've evolved. So we've come exactly full circle in both problems. So to me, the real challenge and I think, for me, excitement is addressing that issue. When did continental crust first begin to form? There's a broad spectrum of my community that say, nope, didn't start until 3.0, 2.5 billion years ago. And then, our lunatic fringe view that, in fact, it's been around virtually since the beginning. Now, the difference between, I could hold in my hand evidence that's consistent with that, whereas I say anybody that, wants to stay with the hellscape paradigm, you got to explain why we're not Venus, right? Why we don't have runaway greenhouse. You want exposed rock and water. Do that. You've got to explain why those Hadean Zircons look so much like they just came out of, a volcano in the Philippines. So, anyway, what I say, that's the I think the big challenge for us in the coming decades.
Are you admitting that you're part of the lunatic fringe? Because I love that.
Well, certainly when we first started reporting these results on the zircons 20 years ago, international meeting, you could hear tittering in the audience, people snickering, because this was absurd, and I'd have to say, the entire community is now on board that there was oceans 4.1, 4.2 billion years ago. Okay? So we've made some significant inroads in some respect, and in others the argument is continuing.
Tell me about that personal side. When you go to these international conferences, your peers, PhDs, the highest levels of academic science, practical science, and you're presenting your theories, your hypothesis, and you hear snickers, and you hear, you see some finger pointing, you see people kind of going like this, oh, that's an idiot, what are you talking about? Personally, how did that make you feel? I mean, did you walk away deflated, or were you like, I don't care, I believe in it, I don't care what they think?
Yeah, I'm, I thrive on that. Okay. And in fact, when, the arguments we made, based on actual empirical data, of there being an early ocean, as that became accepted, particularly in the astrobiological community, I actually felt I had to put the brakes on, which is that, there's certainly evidence, and I keep saying, you might have picked up, water at or near Earth's surface. The actual evidence we have of an ocean at 4.3 billion years ago, there's some evidence for it, but it's argumentative. It's the simplest way to explain what we see is that there has to have been a big aqueous reservoir out here at the surface. But it's not smoking gun evidence. And so whenever anybody, starts to accept what I'm saying, I'm tempted to go in the opposite direction, because in my career, my experience has been that whenever I hear community consensus, I work in the opposite direction because I'm certain that it's wrong.
What advice would you give to aspiring scientists who are just kind of, tiptoeing into maybe this field of study or other areas of science, investigation, entrepreneurship, whatever, about stepping outside of comfort zones and going against the grain?
It's not for everyone. We are social animals, and I used to think science was this culture that existed outside the moral sphere, and I've come to see it very differently now. That this is a complicated sociological system. But I'm going to answer your question in a different way. The thing that worries me about, having these paradigms, yes, there was no continental crust until 2.5 billion years ago, is that we're telegraphing to young people, we know where the moon came from. It was a Mars-sized object. We know that there was no continents until we're telling them that these are solved problems, and they're not. And I'm at the point now. I'm at the end of my career. I didn't solve the problem to everyone's satisfaction. So it's going to be these young minds that we need to harness to do it. And telling them that we know the answer in a highly confident form is counterproductive, because they'll go on and look at problems that might be far less interesting than, what we haven't said explicitly is that understanding Hadean habitability is understanding the origin of life, because life almost certainly emerged during the Hadean. So there has to have been habitable conditions then, and as I see it, we have no other basis to study that than these tiny little ambassadors from that eon. And I did a calculation a few years ago in which I responding to these confident assertions about we know the continental crust origin and growth rate or growth curve, which is that, to my knowledge today, to my satisfaction, we have basically geochronologically characterized 1 million billionth of the Earth's continental crust.
Say that again.
Now, When
Wow.
there are the stories that we've made about, we know, oh no, we know that region, that's Proterozoic, that region there. We do this on the basis of having, actually analyzed, geochronologically characterized, dated 1 million billion of the Earth's crust. When we basically, we get to walk over the top. Sometimes you can drill little holes and get samples, but the crust is big compared to the distance we
Yeah.
can drill holes, and we haven't looked at that stuff down there. And so for us to be confidently, telling the next generation, no, don't worry about the origin and evolution of continental crust. Yeah, we solved that. Plate tectonics started 2.5 billion years ago. I can't say it didn't. Okay, we're limited by the degree to which the rock record wants to cooperate with our scientific endeavors. But what I can tell you is that paradigm the entire community labored under for 50 years is wrong.
Yeah.
So
Yeah.
let's let 1,000 flowers bloom. And if you're shy about not wanting to pick up the tribal chant, this is maybe not the problem for you. But if you're by nature a contrarian, this has just been an immensely fun journey for me. I have no like I say, I have no reason to be able to tell you confidently that continental crust hasn't largely grown since 2.5 billion years. Our data we have is consistent 4 billion years ago, with between 1 and 100% of the present volume of continental crust being then present. So we've got a lot of work to do, and that, say to somebody thinking about a career in earth science, try and narrow down that range of between 1 and 100% of the present volume of continental crust there 4 billion years ago. That's your job, because my generation couldn't do it.
That is fantastic, and I hope that people who are listening to this podcast respond in that way. I do have just kind of a random, this is how my brain works. I just have a random side question. It's not political. I'm asking it from a scientific perspective. This whole fracking thing, when you're kind of cutting through layers of bedrock to try and get, trapped natural gas. From a scientific standpoint, is that a smart idea? Isn't there's a reason there's layers of bedrock there? Is it smart to kind of crack that open because you can't go back down and seal it back up again? Or can it repair itself? I don't know. I just was wondering about that.
Well, in my view, fracking makes a lot of sense, and that until we can wean ourselves of fossil fuels, we're going to need more this material, continuous supply of this material, and if we can do it domestically, then I think we're more secure as a nation. So fracking makes a lot of sense in terms of efficiency, which is, if we're going to get into a liquid hydrocarbon reservoir and pull 50% out of it, why don't we pull 95% out of it? Okay, so I think that's smart. What's not smart is, in fact, letting that material come up to the water table, and then have people's faucets ignite flames when they hold
right
a match nearby. So the fracking doesn't have to mean bespoiling anybody's water table. The fact that we haven't got our act together to prevent that, is shocking, and I think there's a little debate that we shouldn't do that. but
from a geological standpoint, does it hurting anything geologically with the the layers underneath the crust?
No. There's some concern that you can stimulate small earthquakes from that, but you could view it exactly from the other point of view, which is that every little earthquake that you feel in Oklahoma as a result of people extracting liquid hydrocarbons and from underneath them, that's basically stored elastic strain energy. Okay, that isn't there to harm you in the future. So if I could, I would go to the San Andreas and I would, if I knew enough, I would frack the entire San Andreas and then systematically, you know, take that stored elastic energy and dissipate it in a controlled way. Basically have a continuous, magnitude 5 earthquake.
Oh, wow.
And over a long enough period of time, right, you would reduce the potential of having a magnitude 7. Right? I mean, that stuff has been stored in where you are since the Fort Tejon quake in 1857. Okay, the creeping of the Pacific plate past the North American plate is produced this a hazard. So I would rather have it dissipated while I sleep in a series of small earth tremors than I would store it up for a big one. So in some respects, but now the problem is I don't want to be held responsible financially or legally if by doing that I generate the magnitude 7.
Right. There's that.
Yes.
there's that.
There's a way to go down in history.
So, Mark, is there anything that keeps you up at night relating to the Earth, crust, the oceans, whatever's going on, based on your scientific mind and experience?
Not really. I would say that deep time geologists like myself, we don't tend to be alarmists. When I hear statements about how the planet is on a knife edge in terms of environmental conditions, I come at that problem from basis of like, well, it's been a lot worse. It would have been a bad day to be here when the Chicxulub crater was formed 65 million years ago. So I have to say, on balance, deep time geologists make bad environmentalists. But it is the nature of climate change. There's little question that the planet has actually been cooling with a few significant excursions over the last 90 million years or so. And then in the last, 2 or 3 million years, we've cooled to the point where we're now in this series of oscillations that are driven by planetary forcing that plunge us into ice ages. I mean, I occasionally whimsically, when somebody says, "Oh, you're an earth scientist, how do you feel about global warming?" And I say, "Well, I'm for it because 11,000 years ago, my hometown of Vancouver, Canada, was under a mile of ice, and I prefer this better." But there's no question also that in the last 70 years or so, 80 years, that the warming is a great concern. I'm also very skeptical, and so as I mentioned earlier, how the geophysical modelers told us 30 years ago that you can't possibly have plate tectonics early, and so when I see ocean atmosphere models that tell me that there will be a 3-degree increase by the turn of the century, I'm equally skeptical. I think that the models, as sophisticated as they are now, are still simple. They don't they can't account for phenomena that I know of has occurred in the past 20,000 years, extreme temperature changes over short periods of time. So we really don't yet fully understand the ocean atmosphere system well enough to make those predictions. But I mean, there's no question that anthropogenic fossil fuel burning is warming the atmosphere. How and what the complex interactions within that system are, we need to put a lot more energy into that than I think we have. Less energy into depressing the next generation that we're all doomed, and more in better understanding short-term atmosphere-ocean oscillations of just in the past few tens of thousands of years.
I'm curious, everybody knows the Noah story. Is there any scientific evidence that that actually happened? I know it's not internal with water coming out from the center of the earth. It's more about raining and things like that, raining for 40 days a night. But just curious, is there any scientific evidence that the earth was completely flooded and underwater 5,000, 6,000 years ago?
Yeah, a couple of scientists from Columbia University, probably 30 years ago, came forth with a very compelling argument that this was essentially the breaking of an ice dam from the Black Sea flooding into the Mediterranean. And the Gilgamesh myth is widespread in the Mediterranean region. Their view was, to find what a plausible historical parallel. I haven't followed it in the subsequent 30 years, but I don't think it's a coincidence that for example, religions in the Levant and Mediterranean share a watery origin myth. Right? And look at the Genesis verses 1-9. If you're a Hopi Indian in New Mexico, your origin myth doesn't involve floods. I wonder why.
Yeah.
So it's not a surprise to me that Japanese Aboriginal people have a flood myth that where there's lots of water. Water is going to be involved, and if something like that did happen, if there was an ice dam that burst, 7,000-8,000 years ago, that would have gotten a lot of people's attention, and it could well have stayed until the beginning of the fundamental texts of regions, religions.
You talked about the tectonic plates being the reason for the source of salt in the water. How does that actually happen? What's the actual process where that salt is extracted?
It's not so much the tectonic plates as it is now. Imagine, here's your ocean, and now the volcanoes are erupting CO2. CO2 is building up, and the ocean sediments down here, they're not good sucking CO2 down. But now what happens? Look, we got a continent. Now these rocks here. Okay, and let's just for granted, we'll call it for as a model continent. So now there's water out here, it's raining, there's wind driven, and these minerals break down. Now from your trips to the beach that one mineral in that granite quartz is going to break down. It's going to end up basically getting washed and making the sandy shore. But the most common mineral in the Earth's crust, feldspar, it ain't happy out here in the presence of water, and it breaks down. And what happens is the water and the CO2 make an acid, carbolic acid, and that basically, it accentuates this weathering process. Now, when we weather that mineral, we've released calcium. Okay? Calcium and that carbonated water are now in the ocean together, right? The carbon and the calcium make carbon CaCO3. They make calcite. They make limestone. Okay? That limestone. Every time you see a big marble table, okay, or a big limestone reef in Zion National Park, that's sequestered CO2. The carbon in that limestone used to be out here. Okay.
Wow.
And it joined with that calcium. And now, what happens if that limestone, that calcium carbonate, what did that get subducted back into the mantle? We've actually haven't just stored it in the rock form. We've actually put it back into the deep earth, to eventually be vented out in a mid-ocean ridge or a volcano. Okay? So it's the actual subaerial weathering of buoyant crust that's got to stick above the ocean. What crust sticks above sea level here? Well, Hawaii, that's oceanic crust, and it sticks out. But that's small compared to the Tibetan Plateau and the Rocky Mountains. And so it's this interaction between CO2 in the atmosphere an ocean that generates rain, and then when the ocean's getting salty because it's not just calcium, it's the alkali, sodium, potassium, it's magnesium, things like this. They end up in the ocean and they're kind of stuck there. So the ocean's salty because continental rocks weathered earlier in Earth history. And if we didn't have a salty ocean, we wouldn't be drawing CO2 down and keeping this planet nice and temperate.
Mark, thank you for being a great guest on this podcast. I hope that you would be willing to come back on the show and talk more about it sometime.
Okay, well, thank you very much for having me here. And just the last word, I should say that, virtually everything that I speculated on in this last hour, it could be wrong. So I invite you, young people, to in fact, enter this debate. And be the one that proves me wrong. So again, thanks for having me.
Ignition Sequence is produced by Accelerator Media, a nonprofit organization dedicated to inspiring a lifelong pursuit of knowledge. Join us every week as we dive into the science, the stories, and the extraordinary journeys that challenge our understanding of the world. Subscribe now and ignite your curiosity with us. Ignition Sequence. Listen, learn, repeat.